Up until this point, you've seen several aspects of the second law of thermodynamics. We've seen how heat flows spontaneously from hot to colder objects, but not vice versa. And we've also seen that no cyclical process can convert heat entirely into work, and hence you cannot have a 100% efficient engine. So we're now going to concentrate on this third statement here. To understand the second law of thermodynamics at the most fundamental form, we need to understand the concept of entropy. Now, entropy of a system is related to the state of the system, which depends on the system's energy, volume, pressure, and so on. It tells you how many ways that the molecules can be arranged or distributed. So entropy depends on the number of possibilities or configurations. Imagine you flipped a coin. The probability of it landing heads up is 50%. If you flip two coins, then they can land four ways: both heads, both tails, a heads and a tail, or a tail and a heads. So the probability of it landing both heads up is now reduced to 25%. If you flip three coins, you could land 8 different ways, and the probability would reduce down to 12.5%. Imagine if you dumped a whole barrel of coins. The chances of it landing all heads up is possible, but enormously improbable. So entropy is related to the possible configurations. And in a system, that's the possible configurations of molecules. Now, this field is called statistical mechanics and is not really a part of AP Physics B. So really what you need to know is that entropy is the measure of disorder and randomness of a system. For example, a solid has a very low entropy because it's highly ordered all the molecules, like this block of ice shown below. And if this block of ice were to melt and turn into a puddle of water, the entropy would increase because it would become more disordered in the liquid state. You could calculate mathematically the change in entropy of a system when heat is added or removed during a reversible process at a constant temperature in Kelvin by using this formula. Fortunately, you won't have to perform any calculations involving entropy on the AP test. You just have to have a basic grasp of the concept. But it might help you in that, see, if heat is added into the system, then entropy increases. Or if heat is removed from the system, then entropy decreases. We see in the diagram shown below that as the block of ice melts into a puddle of water, the entropy increases. The H2O molecules are fixed in a highly structured and ordered arrangement when they're in the block of ice. However, when the ice melts, the H2O molecules become disordered and unorganized in this puddle of water, and hence the entropy will increase. Now, can you think of other examples where entropy increases, as shown in this question here? For example, imagine you purchase a deck of cards, new cards, so that they're all perfectly ordered. You have ace, 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 then king, 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 and queen, 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 and so forth. And you decide to shuffle the cards. Well, as you shuffle the cards, what happens? They become more disordered, and hence the entropy increases. Now imagine you have a bottle filled up with water and white beads and blue beads that are in two separate layers. What happens as you shake this closed jar? As you shake, the beads become more mixed up and the entropy increases. Or imagine in the corner of a room sits a closed jar filled with argon gas molecules. Well, when the lid is removed, the gas molecules start to move in these haphazard directions into the air molecules. And as they mix with the air molecules, it becomes more and more disordered, and hence the entropy increases. So in essence, all natural processes tend to move to a state of greater disorder. Just like if a cup of coffee, for example, were to fall onto the ground and break into several pieces, the system would be moving from a highly ordered state to a highly disordered state. And this would be a spontaneous process. You wouldn't see these pieces naturally forming back into a coffee mug spontaneously. But you can have situations where the entropy of a system does decrease. For example, this puddle of water can be made back into ice if you were to remove the heat from the system, and hence the entropy would decrease. So when you make ice cubes, the entropy of the water decreases. So we talked about how entropy is a measure of the disorder or randomness of the system, and that natural processes tend to move to a state of greater disorder. There is another part I would like to discuss of the second law of thermodynamics, and that is that the entropy of an isolated system never decreases. And by isolated system, we mean a system that does not interact with its environment. So when it's an isolated system, the entropy will increase or at best remain the same. Basically, the second law predicts that systems will run down, just like this rundown house without a continuous maintenance. And things will evolve towards disorder and randomness, and that complexity will give way to simplicity. However, there are many other examples around you where the entropy decreases instead of increases. For example, plants can grow from simple seeds to complex entities. Or imagine a single-cell fertilized egg grows into a complex adult organism. Over the last billion years, life has evolved from simple unicellular organisms to very complex forms. But they aren't violating the second law of thermodynamics. These self-organizing systems are indeed decreasing in entropy, but they are not isolated systems. For example, a snowflake is a great example where the entropy of the water molecules is decreasing, but the entropy of the universe is actually increasing. Now, these water molecules are becoming highly ordered as they go from a liquid form to a solid form in this crystal lattice. But this doesn't violate the second law of thermodynamics because the water isn't isolated. For it to freeze, heat energy must be transferred to the surrounding air. And there's more of an increase in entropy in the air that surrounds the snowflake than there is in the decrease in entropy of the water molecules. And so the total energy of the water and the air increases as the snowflake is formed. So the key idea here is that the entropy of the universe is always increasing. So as time passes on, our ordered energy is tending to disordered energy. Or you could think of it as the useful energy is turning into non-useful forms of energy.